So my talk could also be titled more concisely, energetically consistent rotated diffusion. So in terms of motivation, there have been a push towards making numerical models consistent with conservation laws of nature. And there have been more and more talk about energetically consistent numerical models or energetically consistent parametrization. Seems to be a big part of the TRR 181. And there is a paper by Karsten and Lars and Dirk, mostly based on a closed energy budget. The way I understand it is that I've been working on these energetic issues of energetic consistency for quite a bit now, and I think that there is still no clear, non-ambiguous meaning of what energetically consistent mean. Because I would argue that even the energy pathways involved in turbulent stratifying mixing are still controversial and not completely settled. For instance, I wrote a paper where I said I disagreed about the common interpretation of energy pathways in turbulent stratifying mixing. But more generally, the problem is that closing the energy budget is not necessarily sufficient to ensure that you will get a more accurate model, because for instance, we neglect viscous dissipation in the temperature equation. This introduces an energy error, but it's irrelevant if the energy error is something like 1 millikelvin per century tendency. That doesn't matter. What matters really is if your energy error is associated with a missing force in the momentum equation. So you can have a closed energy budget, but completely wrong energy transfer. And if you confuse a source of heat with source of work, then you need to be aware that of the difficulty in order to make sure that everything is correct. So for instance, I was involved in this paper, a recent paper, where we try to figure out how to improve energy, the thermodynamic and energy consistency of the atmospheric model, because the tendency at the moment in atmospheric models is to translate any diagnosed energy error. We just add it as heat source in a temperature equation in order to conserve energy. So what you want to do, you want to close your energy budget for the right reasons. So you need to have my framework to think about energetics is based on this one. So basically, I have the mechanical energy budget made up of kinetic energy and available potential energy. And this is what is my definition of work. And then from Lorentz theory, we have the potential energy is the sum of an available part, which is can be reversibly converted with kinetic energy, on a background potential energy part that you can decompose into a gravitational and internal energy part. And so basically, your budget of work, you have a power input by the wind and surface buoyancy fluxes that are dissipated by two main dissipation pathways, one due to viscous dissipation, epsilon k, and the other one by diffusion, molecular diffusion of heat and salt that dissipate AP at the AP dissipation rate, epsilon p, which is the quantity that you use, that you usually regard as 20% of the kinetic energy, but which physically is a distinct process, which serves as a defining KD, the diaphic mixing coefficient. And it happens when you dissipate APE, you have an internal reorganization between gravitational potential energy and internal energy. And for when you have a strongly nonlinear equation of state, this epsilon p and your internal conversion are proportional to epsilon p with this modulation factor psi, which can be equal to 1 for a linear equation of state, but it can be greater than 1, smaller than 1, or even sometimes negative. And so you need to be aware of that the classical linear equation of state picture is quite different from the real, what happened in real fluid. So basically, because mixing the quantity of interest to many of the talks and work presented is related to the AP dissipation, when I move to a numerical model world, I'm going to be interested in sinks of resolve available potential energy in order to estimate whether they are compatible with this AP dissipation rate, which is something that you can measure from either observation of viscous dissipation or from microstructure measurements of temperature variance, for instance. So there are two main things of a resolve AP in coarse resolution model. One is due to the Jantot-McWilliams parametrization, which can be represented as Q diffusion. Q diffusion is the same as advection by mesoscale Eddy induced velocity, which I call VGM, that you can express as a curl of a velocity potential, psi GM. So this is something that flatten isopycnol. So this is well understood how you remove available potential energy, and you do so adiabatically. And then rotated diffusion, where you mix separately along the isopycnol and diapycnol direction, presumably representing the forward AP cascade to small-scale diapycnal mixing. And basically, your rotated diffusion will mix separately the isopycnol component of your tracer and the diapycnol component of your tracer with KD and KI, which are isopycnol mixing and diapycnol mixing diffusivities. So basically, the situation in a GCM, in a numerical model, now that I split the mechanical work budget into resolve and unresolved bit. So you are forced by the wind and surface buoyancy flux as before. And then decay is going to be the dissipation of resolved kinetic energy by a mixing of momentum. And then you have these two things of AP, one due to GM, which is classically interpreted as mimicking about clinic instability energy transfer from mean or resolved AP to turbulent kinetic energy, which is going to be dissipated by epsilon K. And then you have ready diffusion, as going to dissipate resolve AP into presumably a subgrid scale AP, and then ultimately into mixing the AP dissipation rate into heat. So here, my definition of heat is the background potential energy in Lorentz AP theory. So presumably, I must have an internal conversion, but without any information about energy transfer in the subgrid scale. At leading order, you can assume that epsilon K should be approximately equal to the dk plus GM. And you should be able to relate the AP dissipation by ready diffusion to epsilon P, which is a KDN squared. So you can, this is something you can do to test whether your ready diffusion test like it should. So the impact of GM, Jantot-McWilliams on the potential energy has been derived by Stephen Griffiths, for instance. And you can do it analytically with the parametrization of Jantot-McWilliams. So the final result is something like your AP dissipated by GM is proportional to the GM coefficient times the squared slope, where slope is the slope of the neutral vector. So basically the ratio of the horizontal buoyancy gradient over n squared, basically, if you multiply G by, and then there is n squared. Rotated diffusion, we care about the rotated diffusion because lateral stirring is about 7 to 8 orders of magnitude more efficient than vertical stirring. So this necessitates to be careful about how you do your mixing, your lateral and vertical stirring mixing of tracers, because the idea is that if you don't use the correct direction, you will introduce a spurious diapycnal mixing, which is known as the Veronese effect. The difficulty is that there are some ambiguity about the right lateral direction. Has been this is an issue that has been debated for the many places, over 80 years. So I think the ideas about lateral stirring go back to Svedrup et al. 1942, where the author decided that the best direction for lateral stirring, it is if you switch to fluid parcel. The question is how do you do this permutation so that you minimally perturb the ocean stratification and its potential energy? So if you do that, you find that you should the parcel you should do it with two parcels that have the same potential density reference to the mid pressure, which is kind of a discrete approximation of saying that the parcel are stirred along the neutral direction, which are perpendicular to the neutral vector, where alpha, the thermal expansion coefficient, and beta, the Halline contraction coefficient. So McDougall reinterpreted this direction as the direction along which the parcel intersection experience no restoring buoyancy forces. So people have been using the neutral direction as a basis for ready rotated diffusion. And therefore, you can show that isoneutral stirring, by definition, is constructed to leave the potential energy unaffected. So you can do it analytically as well. If you take as your definition of potential energy the volume integral of rho gz dv, and you plug in, you compute the change of potential energy by the ready tensor, you plug in stuff, and you find that there are two terms. One term that is independent, that's valid for linear equation of state, and a term that depends on the nonlinearity of the equation of state. And the isopycnal mixing coefficient only enters the nonlinear term, so, which is due to cabling and thermobaricity, which is a well-known result. But importantly, so the part that exists only for linear equation of state doesn't depend on Ki, the isoneutral diffusivity. So people were happy about that, but the problem is that how do you ascertain that there is no spurious mixing? So the point I really want to emphasize is that mixing, diaphycnal mixing, the existence of it is really related to the AP dissipation rate. That means an AP dissipation rate means that you need AP in order to dissipate it. So in order to get diaphycnal mixing, you need to generate AP and dissipate it, basically. Because it's really, for me, the fundamental definition of mixing. It's not the link to viscous dissipation. There is, of course, a link with viscous dissipation, but this is not really the fundamental one. What you really need to do is to focus on the AP budget, because if you just relate mixing to epsilon k, and if you don't look at the AP budget, you won't necessarily know that whether you do is right or not. So the problem is that if you define if you define lateral stirring as something that leaves a potential energy unaffected, you can still have, if you agree that potential energy has a distinct subcomponent, you can have an internal reorganization between the available part and the background part. And if you do, this typically, if you dissipate APE and you convert background internal energy into background GP, then this is signature of diaphycnal. That means you will have diaphycnal mixing. And if you don't look at the APE budget, if you're just happy to look at a potential energy budget, you won't see this internal reorganization between your subcomponent of potential energy. So in order to look at the AP budget, you can do is to look at, you need a formula for defining available potential energy. And the simplest is to look at the local AP theories that a lot of us have derived over the past decade. And this is simply, you can define it as the integral of the buoyancy between a reference position ZR, where the buoyancy is 0, to the actual depth. And this formula is very general. It's valid for a compressible seawater Boussinesq approximation. The only difference between using fully compressible seawater
5 minutes.
Okay, is different the definition of buoyancy. You can use a true buoyancy or the Boussinesq buoyancy. And in this definition, P naught and 0 naught define your best guess of Lorentz reference state. So basically, you can compute ZR just once you know your reference profile. You can compute ZR everywhere, either in physical space. So here you show that ZR for Antarctic bottom. Antarctic bottom wants to go to the bottom. You can compute it in temperature sanity space, even for points for which there is no data in the ocean. And you can compute the AP density easily. So now the local AP budget, you have an analytical formula. You can derive its budget. So you can show that the local evolution of AP involves a conversion with kinetic energy. There is an impact of a GM. There is a divergence due to diffusive fluxes, and the effect of the ready diffusion is contained in this term, which I called DA previously, sorry. You can rewrite it, you can get rid of the conversion with kinetic energy. And whatever you do, you have this vector PA, which is just a thermoline derivative of the local AP density. And in a recent paper with Gabriel Wolf, I argue these are the correct, these define P neutral direction, which are the direction truly defining lateral stirring direction, minimally perturbing the AP in the ocean. So if you look at the effect of GM on the AP, you find exactly the same result as for the total potential energy. So as far as GM is concerned, the effect of GM on AP on potential energy is exactly the same. So there is no issue. You don't create a Veronese effect. It's a purely adiabatic, as people know. But if you do it for ready, then you find that the impact of ready diffusion on AP is very different than the impact on potential energy. And it shows that now you have a strong dependence of the isopic. There is, like for potential energy, there is a term depending on a linear equation of state on a non-linear term. So here I discuss only the term valid for linear equation of state. So for potential energy, there was no dependence on Ki, but for APE, there is. And this dependence on Ki depends on the angle between the neutral vector and the reference neutral vector, which is a direction perpendicular to the Lorentz reference density surfaces. And this angle becomes very large in the Antarctic circumpolar current. So basically, the prediction here is that this term, the whole term, won't look like epsilon p kd n squared in the Southern Ocean. And you can predict it. So if I took the ratio, I can just using standard value for Ki and Kd, and I can estimate this term. I have an analytical formula, so I can use data, estimate it from data. I can compute the ratio of this dissipation, ready dissipation over Kd n square, which is my kind of metric of what's correct, what I expect. And I find that in the Southern Ocean, I have about 10 times too large AP dissipation. So now I can relate what's interesting because people have, like Forget, estimated the sensitivity of the stratification to Ki and found that in the Southern Ocean, the stratification is very sensitive to Ki. So is it really something real or an artifact of the ready rotated diffusion using neutral direction? Another issue for which it's important is that if you look at the sensitivity of the ACC transport, if you use a very high value of Ki, you get a very weak Antarctic circumpolar current. So you have and there is a paper recently by Ashvita, Manita, Karsten, showing quite a strong sensitivity to isopycnal diffusion. Again, I'm asking the question, is that real or an artifact of a neutral rotated diffusion? So to summarize, I want to make the point that diaphycnal mixing relates to the AP dissipation rate. So in order, it's really important to look at the AP budget in order to test, to establish the energetic consistency of mixing parametrization. So here I discuss the case of isoneutral mixing, showing that if you just look at the potential energy budget, you are missing the fact that the impact of ready diffusion on AP is very different from the potential energy, and you won't see that there is a Veronese effect associated with neutral diffusion. So my point is that neutral direction are not the right direction to use in rotated diffusion. What is the right way to do it is difficult because there are many complications due to the fact that double diffusion complicates the picture, and it happens there is a coupling between lateral and vertical stirring, which means that there should be some sensitivity to Ki. So to be continued in order to understand how to do it properly. We stop here. Sorry if I run over time.
Thank you.